Hello, everyone. Depending on where you are, good morning, or good afternoon, or good evening. I am Professor Glaucio Paulino from Georgia Tech. It is my great pleasure to introduce to you the next plenary speaker of the Combined Engineering Mechanics Institute and Probabilistic Mechanics and Reliability Conference. Today, I am very pleased to introduce to you my very good friend, Professor Katia Bertoldi. She is the William and Amy Kwantanoff Professor of Applied Mechanics at the Harvard John Paulson School of Engineering and Applied Sciences. Katia obtained her combined bachelor and master degrees from Trento University in Italy in 2002. She then obtained another master degree from Chalmers University of Technology in Sweden in 2003, and the PhD in mechanics from Trento University in Italy in 2006. Then she went for a postdoc at MIT. Afterwards, she became an assistant professor at the University of Twente at Netherlands. And finally, she joined Harvard University in 2010, where she presently is. Katia is the editor of a couple of journals in mechanics, including Extreme Mechanics Letters and the Journal of the Mechanics of Materials and Structures. She received several awards in her professional career. I just list a few over here. Those awards include the Hughes Young Investigator Award and the ASME Journal of Applied Mechanics Best Paper Award, both in 2014. She also received the NSF Career Award in 2011. And she is presently a member of the board of directors of the Society of Engineering Science. A few years ago, I was fortunate to serve together with Katia in the SES board. A few highlights that I would like to point out is that a few years ago, Professor Harry Dankovics, the editor-in-chief of Applied Mechanics Reviews, interviewed Katia and created a podcast that is available in the journal website. The podcast is very interesting, and it highlights Katia's journey since the time that she was an undergrad until the time that she became a professor at Harvard. The podcast is very interesting, has a few very nice stories, and one of the stories that called my attention is that sometimes great research happens with no predefined plan. For instance, Katia's fascinating early work on geometric instabilities was created as a series of serendipity facts that happened that ultimately led to the great research that she did. So I will not spoil the story so that you will become very curious and eager to listen to the podcast. Another highlight is Katia's website. It is a very nice website, very informative, and has several videos and very good information in mechanics in general, and I strongly recommend that you explore her website. Katia has very diverse research interests, and I just summarized a few of them here. Those research interests include the design of materials with carefully architected microstructures that lead to novel effective behavior at the macro scale. She also looks at the mechanical and acoustic properties of structured materials with a particular emphasis on harnessing instabilities and very strong geometric nonlinearities to generate new modes of functionality and behavior. And this is a topic that she will explore today during her plenary lecture. Moreover, since the properties of the architected materials are primarily governed by the geometry of the microstructure, as opposed to the chemistry or the constitutive ingredients at the material level, then the principles that she discovers are quite universal and can be applied to systems over a wide range of length scales with a diverse range of applications, including, for example, energy dissipation, focusing, and waveguide. So today, it is my great pleasure to introduce to you Professor Katia Bertoldi, who will talk to us about multistable structures from energy trapping to morphing. Katia, you have the floor. Let's hear Katia's lecture. Thank you very much.
Good morning. It's a pleasure to join you. Clearly, I would have loved to give this talk in person, but this year, unfortunately, this was not possible. Let's hope that next year we can go back and enjoy in-person conferences. So in this talk, I want to share you some of the some recent results from my group. And it's going to be a talk about structure, in particular about multistable structures. So for millions of years, nature has used structure to achieve a new, unusual, extraordinary property. Think of the sponge. On structures, microstructures has been demonstrated to provide robustness. Structure has also been used by nature to create colors, as well as to enable adhesion. So these are examples from nature, but also us, humans, we have been using structure to enhance the properties of material. And here is a very simple example. So over millennia, we have been able to move from pyramid to this incredible skyscraper, all making use of geometry, taking advantage of geometries. But clearly, structure are not only buildings, are not only bridges. Structure is everywhere, surround us everywhere at different scales. An umbrella is an example of a deployable structure, but we also have designed structure to absorb and direct sounds. We use structure for packaging to protect objects, as well as to direct light. And this clearly is a photonic structure that in this case is at the micrometer scale. So in my group, we are very excited about structures. And what we do, we combine theoretical, experimental, and also computational method to design highly deformable structure, and we try to take advantage of deformation to achieve new modes of functionality. And here you can see some examples. So we have been using instability to design material with unusual properties, such as negative Poisson ratio, to design energy absorbing material, as well as actuators. And we have been also using origami principle to design reconfigurable structure, as well as to we have been using bistable mechanisms. We have been studying propagation of mechanical signal through this nonlinear system. So, and today I want to focus on a special class of structure, and these are multistable structures. So the structure I'm going to talk about are elastic structure, so a structure made of elastic material. And typically when we take an elastic structure, as the structure you can see here, that is made of a rubber, we compress it, it deforms, it might undergo substantial deformation, but as soon as we release the load, this goes back to the initial configuration. And this is because the force displacement curve may be highly nonlinear, but the potential energy, the energy landscape is characterized by a single minimum. However, we also have known for a long time that we also can design an elastic structure to have two stable configurations. These are the so-called bistable structure. And this here you can see an example. In this case, it's a thin shell, and we give it the shape of a dome. And now you can see that we push it down, but as soon as the finger gets away, it goes back to the initial configuration, but it retains its inverted shape. And why is this? Well, because this structure is characterized by the energy of the structure is characterized by two minima. One that corresponds to the undeformed configuration, one that corresponds to a stable deformed configuration. Now, for many years, the mechanics community has studied how to identify and realize shapes leading and elastic structure leading to bistability, to multistability. But in recent years, also a new trend has emerged. And specifically, multistable structure have emerged as a powerful platform also to design to engineer new functionality and to design smart structures. And here I'm reporting 3 examples. So on the left here, you can see an early example from Doug Holmes at BU, where he has used the bistability of dome-type shells to realize tunable lenses. The center is work by Lorenzo Valdevit at UC Irvine, where he has used multistability to engineer significant shape changes. And on the right is work by Chiara D'Araio. And in this case, bistability has enabled propulsion of a simple robot. And my group in recent years has been thinking about these lines. And today, specifically, I want to talk about 2 specific projects. So in the first project, we'll see how bistability can be exploited to design large-scale inflatable origami structure and deployable origami structure. And in the second project, in the second part, instead, we look at the behavior of arrays of bistable structure, and we'll see how these also provide an opportunity for robotic systems. All right, so let's start focusing on the first project on bistable deployable structures. So here, our goal is to design deployable structures. So what are deployable structures? These are structures that have a compact state that is ideal for transportation and storage, and an expanded state that is used for functionality. And here you can see an example of linkage-based deployable dome. And the guy here that you can see here is Chuck Oberman, and the project I'm going to present is work in collaboration. It was led by my postdoc Ben, my student David, and it was and it's a collaboration with Chuck Oberman. So now, if you think a deployable structure, there are a number of features that we would like them to satisfy. So first of all, we want them to occupy the minimum space when they're folded. We want also to provide a robust shell, a protective environment when they are deployed. We want them to lock in place after deployment. We want them to retain the deployed shape. And finally, we want to be as easy as possible to deploy. So keeping in mind this requirement, then we started looking for solutions that satisfy them. Clearly, there are solutions out there, and one you can see here, and for example, linkage-based structure, but they don't satisfy all these requirements. For example, for linkage-based structure, in order to provide a robust shell, you need to have a cover that typically is a separate component that then you add on. And further, also to lock them in place after deployment, typically you need to add additional components. So we started thinking about a platform that enables us to pretty much, satisfy all these requirements. And origami came to our mind as a promising platform. Why is origami a promising platform? Well, first of all, they occupy, these are structures that, can go from a very compact configuration to an expanded configuration, as you can see in these movies that are playing here. And so, and second, they also naturally provide a robust shell because, naturally integrated faces and hinges. All right. Further, it has also been shown that by carefully designing the folding pattern, they can be designed to be bistable, to have multiple stable configuration. And so this feature can also, we envision this feature can be exploited to be able to lock in place our structure after deployment. So all this is good, but how about easy deployment? So the deployment on origami is not typically so easy, as you can see in this movie at the center of the top row. Typically, in order to deploy them, you need to control individual hinges, and this makes the actuation quite a complex process. So to overcome these challenges, here, we thought about inflatable structure. And we use inflatability because this is a inflatable structure are very easy to deploy. So all you need to do is to provide an input pressure and then automatically they deploy. So then our goal is, our question is, okay, can we design origami structure that are, can we use origami principle to design deployable structure that are bistable and inflatable? All right, so what is our platform? Our building blocks is extremely simple. It's a triangle, ABC, alpha and beta are the internal angle. And then what we do, to deploy this triangle, we rotate it around the edge BC. And here is a very important, very simple and important property that is at the base of our concept. So if we choose the internal angle beta to lie within these limits, at a certain point during deployment, vertex A will intersect again the circle circumscribed to the flat configuration, to the initial flat configuration at a certain point. And why this is important? Well, this means that the angle alpha is recovering the projected XY plane. And remarkably, these simple properties give us opportunity to realize close origami structure with at least two stable configuration. And why is this? Well, so we can take a triangle and now we can tessellate to form a closed structure. So what we know is that this triangle, now we know that it recovers the angle alpha at a certain point, at a certain level of deployment. And so it means that this structure has also another geometrically compatible state that is expanded. It's a deploy compatible state. And now you might ask, okay, what's in between? Well, all configuration in between are going to be geometrically incompatible. And here the incompatibility is highlighted in red. So it means that the faces are either going to separate or are going to compenetrate. And we can geometrically quantify this incompatibility. And here I denote this geometric incompatibility, will denote this geometric incompatibility by delta ABC. So the idea is these simple geometric properties will provide opportunities for bistability. And why is that? Well, when we make this structure out of elastic material, the flexibility intrinsic of the structure will absorb this geometric incompatibility. And so the idea is this structure will have two stable configuration in correspondence of the compatible states, the flat compatible and deploy compatible states. And these two states are going to be separated by an energy barrier generated by the deformation caused by this geometric incompatibility. All right, so let's learn a bit more about the deployment of a triangle. So here I'm focusing on a triangle with alpha equals 30 degrees and beta equals 33 degrees. And what I'm reporting is the evolution of the incompatibility as a function of the deployment height of a vertex A. So we see that there are two stable states, and one clearly is the flat state, and one is the expanded state at which the incompatibility is equal to 0. However, if you remember, our goal is to design bistable structure that are inflatable. So we also look at the volume under the triangle, and this is denoted here with VABC. We can easily calculate that based on simple geometry. And now here I report in the evolution of this volume as a function of the deployment height. But now we see there is a problem. Why is there a problem? Well, the maximum volume happens before the expanded compatible state. So what does this mean? It means that the expanded compatible state cannot be reached through inflation for this specific triangle. Is this a universal property? Well, here I'm considering another triangle with alpha 30 degrees and beta 50 degrees. In this case, we see that the state of maximum volume occurs after the expanded compatible state. So the expanded compatible state can be reached by inflation. However, we can see that the level of geometric incompatibility is very low. So the idea is such triangle will give rise to a marginally bistable structure. So is this universal? Well, what we can do, we can quickly scan the entire design space, since we have close expression to characterize both bistability and the volume. So, and what we see is that if we want to realize a structure with a large geometric incompatibility, we need to use triangle close to the upper boundaries of the domain. On the other hand, if we want to realize structures that are inflatable, we want to use triangles that are close to the lower boundaries of the deployable of the domain. All right, so this pretty much tells us that if we want to realize structures that are inflatable and bistable, we cannot use a single triangle, but maybe there is opportunities to realize inflatable and bistable structure by combining several triangles. And so this is what we are going to explore next. So first, what we do, we take two different triangles and we put them next side by side to realize a star-like shape. And then we put two layers, one on top of each other, to realize a closed shape. And now what we can do, we can characterize the incompatibility, the maximum incompatibility and the inflation constraint for many of such designs. And what we see is that the incompatibility monotonically decreases as the inflation constraint increase. So now what the question is, we can focus on the inflatable design with the largest geometric incompatibility, design A. And now the question is this structure going to be bistable? So to answer this question, we go to the lab, we fabricate the structure. So we use, we 3D print the faces, and then we use thin a plastic sheet to realize the hinges. And now what we see, we make sure the structure is airtight, we inflate it, and then we remove the input. And what we see is the structure immediately deflated, goes back to the initial configuration. And at the same time, during our test, we also record the PV curve. And we can see that for this specific structure, there is no sign of bistability. So we have a monotonic PV curve. All right, so what this tells us is that given our fabrication strategy and the material that we use, this level of maximum incompatibility for design A is not enough to guarantee bistability. So what else can we do? Well, what we can do, we can still put the triangle next to each other, but instead of connecting the long edge of the triangle to the long edge of the other triangle, we can connect the long edge of a triangle to the short edge of the other triangle. And when we do that, what we see is that we increase the level of maximum incompatibility. So to see whether next, we check whether this is enough. So we focus on design B, that is the design, the inflatable design with the largest level of geometric incompatibility. And we fabricate and we test it. And so here you can see the experiment. So David is going to inflate it. And then he's going to remove the input. And what we see in this case, the deployed configuration is retained. The structure doesn't deflate back, even when it's at atmospheric pressure. And this bistability is also confirmed by the PV curve. We see is non monotonic and characterized by an area of negative pressure. All right, so at this point, we have a strategy to design bistable and inflatable structure, but we are also limited to this star-like shape. So to expand the type of shapes, what we can do, we can also put, instead of putting the triangle side to side, we can put the triangle on top of each other. And when we do that, we realize this wedge type structure. And what we see is that structure are characterized by even higher geometric incompatibility. So we can go and fabricate one of these designs, specific design C. and we can run, we can inflate it. And during the inflation, we can measure the pressure. And what we can see also in this case is sort of expected. We can see a large region of negative pressure, and we can see that the structure is bistable and retain the shape, even the expanded shape, even after the input pressure is removed and it reaches atmospheric pressure. All right, so now we have another building block that is inflatable and bistable. So far, all these building blocks, they start flat, they have a flat configuration and expanded configuration. But what we can also do, we can realize building blocks that go from one expanded configuration to another expanded configuration. And why is that? Well, we can think at the flat triangle as the projection of an initially rotated triangle. And interestingly, in this case, we have one more degrees of freedom in the design, that is the initial rotation of the triangle. And what we can show is that we can realize bistable and inflatable structure using a single triangle, a single building block. And what you can see here is that these structures are characterized by large values of maximum geometric incompatibility. So also in this case, we can fabricate the structure at the centimeter scale, and we can test them, we can inflate them. And what we see, we can, they are largely bistable and characterized, the PV curve are characterized by a region of negative pressure. All right, so at this point, up to this point, what we've done, we have identified, we have been looking at 4 different designs comprising 2 different types of triangles. And what we have seen is 3 of them can be bistable and inflatable at the same time. All right, on the other hand, at the beginning, I was promising you functional, bistable, deployable structure, right? And clearly, we cannot see that yet. But on what we can do now, we can think of this design as building blocks to realize functional structures. So, for example, we can focus on design 3, so this wedge type structure. And by combining 2 of such design, we can think of realizing an inflatable arch. And so here is our prototype and experiment. So this structure is slightly larger, it's at the meter scale, and is realized out of corrugated plastic. And so now you see we have inflated the structure, we have deployed our arch, and now we are removing the input pressure. So soon the inner cavity will be at atmospheric pressure. But what we see is that the structure remains in the expanded configuration. So this confirms the bistability. All right, so what else can we do? We can also combine layers of different design to realize functional systems. So for example, what we can do, we can use a layer of design 1 and a layer of design 4 to realize a tent, a shelter. And the layer of design 1 will define the floor, and the layer of design 4 will design the livable space. And now in the prototype we build, we also, to improve the livable space, we also use trimming operations. So we use 3 different layers of design 4, but this doesn't change the working principle. It's purely for aesthetic reasons. And so what we envision is a structure that is initially flat, then we provide pressure, is going to deploy. And importantly, when we open the door, so we bring the internal environment to atmospheric pressure, we're still able to retain its deployed state. And so here you can see David and Ben with our prototype. So it's flat. Now what they are doing, they're connecting the pressure source. And so we are pressurizing the structure, and we see that it's deploying. And now the roof is deployed. And now David goes in, he opens the door. Now the structure is atmospheric pressure, but it doesn't collapse. And this is because it's bistability. And now when, we are done using the structure, we can simply connect to vacuum. So we can bring it back to the flat state and we can move it. All right. So here is pretty much where we are with this project, with the design of deployable and inflatable and bistable structures. So in the second part of this talk, I want still to focus on bistable origami structure, but this time I want to focus at arrays of bistable structure. And what we'll say is that how we can program such array to realize simple robotic systems. So what you see here is a robot designed and realized at Boston Dynamics. And you can see these robots are incredible. They jump, they can run, they can do all sorts of crazy movement. But clearly these machines are also extremely complex and extremely expensive. And the complexity of this traditional rigid robot in recent years has motivated the search for inexpensive and simple machines that are still capable of functionality. And typically these machines are made of compliant materials such as rubber. And here you can see three examples. So you can see these simple machines are able to grip objects, they can move, and they can, since they are made of compliant material, soft material, they're also good to interact with humans, and for example, they've also been exploited to realize medical devices. However, as you can, lot of progress has been done in the past few years, but there are still challenges that remain. For example, you see that, you know, if we have a gripper, this gripper can only bend, right? We design an actuator, and this actuator is only able to achieve one configuration, to deform according to one configuration. So the question we can ask is, can we design an actuator that can achieve a different set of configurations, that can bend but can also twist when actuated with a single input? So depending on the level of input, it can achieve different deformation. Or can we also design a system that is able to move when actuated with a simple input? So as you can see in the movie over here, you see that in order to achieve locomotion here, there are many tubes coming in. And why is that? Well, because in this actuator, we have, in this simple robot, there are 5 actuators, and they need to be actuated independently according to a specific sequence in order to achieve locomotion. So to address some of these questions, we have recently explored a simple origami platform. Specifically, we have focused on an origami module based on the Kreslin pattern. And again, we have been using inflation as our stimulus. And so here you can see our simple basic Kreslin pattern is not bistable. This pattern can also be designed to be bistable, but we designed it to be, we chose a geometric parameter so that the system is monostable. So you see we pressurize, it twists and expand, and then we vacuum it. It's basically inflate, we deflate and go back to the initial configuration, to the flat configuration. So in order to achieve functionality here, again, we explore bistability as a platform. And so in order to make our building block bistable, what we do, we divide one of the panel into 4 triangles to form a 4-type vertex. And here you can see one of our bistable unit cell. You see, so when we inflate, you see that our bistable panel pop out. And then, so this means that when we inflate, first the panel remain out. And so this breaks the rotational symmetry and makes, basically introduce bending. And then finally, when we further vacuum it, also the bistable panel pop back in, and then the structure goes back to the flat state. All right. So here is our monostable, the simple Kreslin unit, the monostable one. Here is the state diagram for our bistable structure, where you see if the inflation, we inflate large enough, we can pop up the panel, and then when we deflate, we can achieve some bending because of as we break the rotational symmetry. So an important point here, we can control the pressure at which the bistable panel pop out and pop back in by tuning the position by controlling the position of the central vertex. And here we denote with delta such a position, and we can see that by increasing delta, we can increase the pressure required to snap the panel, the bistable panel, both when inflating, and we can also increase the threshold for the vacuum. As for the maximum bending angle that we reach, we see that this is insensitive to delta, and this is because it's determined by the contact between the rigid plates. Okay, so now we have found we have a strategy to design a bistable Kresny unit. So now we have a strategy for designing a bistable Kresny unit. So what we can do during our experiment, we can also measure the bending, the twist, and the displacement for the different building block with different levels of delta. And then we can use this measurement as a base for a very simple geometric model, where we can that we can use to predict the behavior of stacks of such modules. So, and now when we stack this unit, what we can, the parameter we can play with are the delta for the different units, but also the orientation of the unit, so the chirality of the unit, as well as the position of the bistable panel on these units. And so just to test our method, so here we focus on a simple two-unit structures. And now this is the state diagram that we predict based on this geometric model that use the data that we collect for the single modules. And then here is what we measure in the lab when we built this prototype by connecting two different units. So now, our goal is to use these stacks of units as a base to realize simple robots. So we are particularly interested in the deformation that this structure can achieve. And so what we do, we also quantify the deformation associated to each of the stable states. And specifically here, I'm reporting the distance between the two caps, the central point of the two caps on the vertical axis, and the angle between the vector that connect the two ends cap in the XY plane for all stable configuration. And what we can see is more configuration are straight, are characterized by theta equals 0. But under vacuum, there are some configuration characterized by a significant bending angle. So next, what we can look, we can combine this with a very simple optimization algorithm to try to design an array of building blocks capable of, for example, reaching 3 specific targets that here I denote with T1, T2, and T3. And so what we do in order to identify the design leading to a actuator that capable to reaching these 3 targets, what we can use, we can combine our simple geometric model with a very simple optimization strategy. Here we use a greedy algorithm. And what this algorithm enables us to identify is the optimal configuration. Specifically, tell us that if we want, in order to design a target actuator that reach this 3, that gets very close to this 3 target, it's best for us to use to stack together 12 units, and it gives us the specific of each of the units. And then here is the state diagram for such an actuator. And what we see is first we need to inflate it up to P4, and then when we deflate it, we can reach the first target. Then at this point, if we want to move to the second target, we need to reset the system and then pressurize it a bit further and then vacuum it. And in this case, we reach first T2 and then T3. So that's the prediction of the model. So let's see how it works in practice. So here is our robotic arm. So now we are pressurizing. So with some of the panel pop up, and now we are depressurizing and we reach T1. At this point, what we are doing, we are resetting the system. So the actuator goes back to the initial configuration, and now we pressurize it further. So when we vacuum it now, we can reach T2 and subsequently target 3. And then we reset it and we go back to the initial configuration. So in this case, we have been able to realize a system that can achieve 3 specific deformed configuration at 3 different levels of applied input. However, for this case, in order to achieve the 3 targets, we need to reset the actuator in between. And this is not always convenient. So if you think about locomotion, we want to have a loop, right? We want to have a trajectory. So what we can do, we can also add additional constraint into our optimization algorithm to require that, to basically require that there is no reset in between the targets. And so when we impose that, here you can see we get a different optimal configuration. And this provide opportunities also for closed loop that, for example, can be used for robotic locomotion. So just to demonstrate the concept, so now our goal is to realize a simple robot that can propel itself. And so for this, we take inspiration from the closed trajectory of our rowing stroke. And so here are the 2 targets in this case that we want to our actuator. So we want first to move to T1, straight, T1, and then T2. And so again, we use our optimization algorithm. In this case, we found that actuator with 3 units is best to move between these 2 targets. And here is the state diagram, and we can see we need to pressurize above P4, and then when we vacuum, we'll get first T1 and then T2. So now we have the actuator. How do we go from this actuator to a robot? Well, what we do, we mount 2 of these actuators to a chassis, and we attach them to the actuator also 2 rigid rods that act as amplifier, and so to enable basically the actuator to touch ground to propel itself. And so here is the idea. So when we reach T1, the rigid arm, the amplifier, will touch ground. And then when we move from T1 to T2, we'll take off. And so this will propel our robot. And here is a movie of our simple robot in action. And what we are providing is a single input pressure. So we are pressurizing and depressurizing the actuator. And we see that over the cycle, each cycle, the robot propels itself, moves a bit toward the left and finally. And so by cycle, it keeps moving. And okay, so this brings me to the conclusion. I hope I convinced you that bistable structure, bistable element offer a promising platform to design mechanical system with new mode of functionality. Specifically today, I've been focused on deployable structure and robotic system, but I'm sure there are many more functionality out there that are waiting to be explored. And if you're interested about this project, here are the 2 papers where you can find more detail. Thanks for the attention.